Let's simulate this circuit and see what is maximum power transfer theorem. Okay, here I will change the load resistance RL and we will record the value of voltage and the value of current. Here you can see I connect a ammeter to record the load current and connect a voltmeter with parallel with the load resistance to record the voltage. If we record the source voltage and the source current, then we will get the power delivered from source. Okay, and if we multiply the load voltage with load current, then we will get the power received at load. Okay, here you can see the load resistance is 5 ohm. Okay, and for the load resistance 5 ohm, the load voltage is 5 volt. Okay, so record this value. Load current is 1 ampere, source voltage is 7.5 volt, and source current is 1 ampere. Now let's change the load resistance value from 5 ohm to 4 ohm. Here you can see the load voltage decreases from 5 volt to 4.62 volt, but current increases from 1 to 1.15 ampere. Okay, and the source voltage is 7.5 is same for all. As if I change the load resistance, source voltage will be constant. Okay, so this source current and this load current will be the same. Okay, now you can see the source current also is 1.15 ampere, right? Now let's change the load resistance from 4 ohm to 3 ohm. Okay, now the voltage is 4.09 volt load voltage, load current is 1.36 ampere. Okay, the source current is the same as load current is 1.36 ampere. Okay, now let's change the resistance from 3 to 2.5 ohm. Here you can see the load voltage is 3.75 volt. Okay, and load current is 1.5 ampere. So source current will be 1.5 ampere. And let's change the resistance from 2.5 to 2 ohm and 1.5 and 1 ohm. Okay, and then you will get the data like for 2 ohm will be how much? 3.33, and the current is 1.67. Okay, and for 1.5 ohm is 2.81 and the current will be 1.88. Okay, and for 1 ohm the load voltage is 2.14 volt and source current is 2.14 ampere. Okay, so now we already got the values of load voltage, load current with respect to the load resistance. Okay, if we just multiply this voltage and current, then we will get the power. So let's do that one. So from here you can see that when the load resistance is same as the source resistance is 2.5 ohm, at that time you can see the maximum power is delivered to the load, right? And at that time the percentage of power received at load is the 50%. Okay, so that means when the maximum power transform happens, at that time the power transfer from source to load is 50%, and at that time the load resistance is same as the equivalent source resistance or Thevenin resistance. Okay, so now let's go to the next slide and see the curve. Here I plot the load resistance with the load power, and you can see if I change the load resistance from 1 ohm to 5 ohm, the curve looks like this one, right? When the load resistance is same as source resistance, at that time the power is the maximum, and this value is how much? Is 5.625. And if you see the bottom curve, at that time you can see percentage of power shared from the load or transferred from the load is varied. Like when we increase the resistance, at that time we can see the percentage of power received is increased, right? But ultimately, when the load resistance is 5 ohm, at that time the power is less, is only 5 watt. But the percentage received is much higher, is around 60%, more than 60%, right? 66.7%, right? But so we don't care about how much percentage of power coming from the load, right? We need to care about how much the power we received, not the percentage, is the magnitude. Here you can see when the value is 2.5, the load resistance, at that time the percentage sharing is 50%, right? But the maximum power we received is 5.625 or 5.63 watt. So from the simulation point of view, we prove the maximum power transfer theorem. Now let's go to the theory and calculation, and I will prove that the maximum power will transfer from source to load when load resistance is same as the source resistance or same as the Thevenin equivalent resistance. Okay, so let's go to the calculation. We already did the Thevenin's theorem and Norton's theorem, and Thevenin's theorem states that any linear bilateral network black box, any linear bilateral network can be converted to a voltage source VTH with the series resistance RTH and the RL, right? Now we need to know the maximum power transfer theorem. Maximum power transfer theorem states that the maximum power is transformed from the source to the load when the value of load resistance is exactly equal to the value of the RTH. Okay, this is for the DC. Okay, for the AC, the theorem is the same, but the equation is different. Now we need to prove this maximum power transfer theorem. From here you can see this load current is IL, right? And we can write down IL equal to VTH by RTH plus RL. Okay, and we can write down power L, PL is the load power, is equal to load current square multiplied by RL, right? I square R. If we replace the RL, then we can write down VTH by RL plus RTH square multiplied by load resistance. This is equal to load power. Okay. Now, maximum power transfer theorem states that when the RL equal to RTH, this will be max, right? How to calculate that one or how to prove that one? We need to do the differentiation of load power with the load resistance, and that should be equal to 0 to find out the condition for the max or min, right? Now, what do we need to do? We need to do the differentiation of this equation with respect to the load resistance. Okay, now go to the next page. So, load power equal to VTH divided by RL plus RTH whole square multiplied by RL. Okay. So from here we can write down PL equal to VTH square multiplied by RL by RL plus RTH whole square. Here VTH is not a function of the load resistance, right? That means we can consider VTH as constant. Okay. Then do the differentiation dPL divided by dRL is equal to VTH square constant d by dRL RL divided by RL plus RTH square equal to 0, right? So from here we can write down d by dRL of RL by RL plus RTH whole square equal to 0. Okay, go to the next page. D by dRL RL by RL plus RTH square equal to 0, right? Now just need to do the differentiation. We can consider this as u by v, right? So we can do it like this: RL plus RTH whole square, third square month, that means 4, okay? And u del v, right? That means RL into 2 into RL plus RTH minus RL RTH whole square into 1 equal to 0, right? From here we can write down 2RL square plus RL 2RL RTH minus RL square minus 2RL RTH minus RTH square equal to 0, right? 2RL to RTH is cancel out. From here we can write down RL square minus RTH square equal to 0. And from here RL should be equal to RTH. We cannot consider it minus, right? Why? As the resistance cannot be minus here. So RL should be equal to positive RTH. So, hence proof, the maximum power will delivered from source to the load resistance when the load resistance is equal to the Thevenin resistance. Okay, this is for the DC. AC is different. Okay, now suppose let's consider a problem. This one 15 volt, 5 ohm, 5 ohm, and they say this is RL. Okay, and they told you find out the value of RL such that the maximum power will flow from the source to load, right? So what you need to do? You already know, right? RL equal to RTH. So you just need to find out the value of RTH. So value of RTH will be, we already know this one. This is ohm meter 5. That means equal to 2.5, right? That means the RL should be 2.5 ohm such that the maximum power will flow from source to load, right? Now we need to calculate the value of maximum power. So we can write down P max will be how much? We already know P max equal to VTH by RL plus RTH square into RL, right? Here RL equal to RTH, that means VTH divided by 4 RTH, okay? The square multiplied by RL or RTH, okay? If we just replace this one, we can write down P max equal to VTH is how much? VTH will be, I already calculated in my last video, VTH will be 7.5 volt, right? So VTH will be 7.5 volt divided by 4 into 2.5 multiplied by 2.5, okay? So this will be 3 watt, okay? So in the maximum power transfer theorem, the maximum power can be delivered to the load will be here 3 watt, okay? And the maximum power you can deliver to the load always should be 50%, okay? As here you can see, if I draw the equivalent resist circuit, then here we have the RTH, right? And here we have the RL. So 50% power consumed by this equivalent resistance and 50% power will consume by this load resistance, okay? So the maximum power can be delivered from source to load is equal to 50%. And when we can achieve this one? When RL equal to RTH. Okay. So that's all for this maximum power transfer theorem. Okay. See you in the next video where I will do the previous year question from the circuit theory. Thanks for your time. Please do share this concept with your friends. And if you like this video, please press the like button. It is really means a lot for me. Bye bye.